all, Ali Hamdan, member of the public relation pillar in the Lebanese oil and gas business network. First, I would like to welcome you to the third event of our pillar. Our guest is Dr. Kamel Hamdan. He holds a PhD in petroleum engineering from the University of Aberdeen in UK and a master's degree from Hydrocarbons University. He also completed his BE in Power and Control Engineering from BAU and currently is an assistant professor in the Chemical and Petroleum Department of in Beirut Arab University. Engineer Leen, the head of this pillar, will moderate this session. And now, Leen, the floor is yours.
Thank you, Ali. As Ali mentioned, I'll be moderating this webinar. And we are so happy as a public relations pillar to have Dr. Kamel Hamdan as our guest speaker for today in order to discuss an introduction about hydraulic fracturing. And at the end of the presentation, we'll have a 15 minutes QA as usual. And Dr. Kamel, the floor is yours.
Okay, thank you, Ali. Thank you, Leen. So today we're going to present an introduction about hydraulic fracturing. So the outline of this presentation is going to be as follows. Since this presentation is for the general public, so anyone could be participating, whether he's petroleum engineering or he's not. So we're going to start with where can we find hydrocarbons. After that, we're going to talk about the difference between conventional and unconventional reservoirs. Once we get that sorted out, we're going to talk about hydraulic fracturing. So what is hydraulic fracturing and what are its applications? Then we're going to cover the design, the major design parts for hydraulic fracturing in terms of the orientation of the fracture, the fluids and the chemicals that are used. Proppants, if you don't know what proppants is, we are going to cover it. Multistage completion as well. So I'm sure you have heard something called multistage hydraulic fracturing. So we are also going to cover that. And finally, we are going to talk about the impacts of hydraulic fracturing on the environment. So first thing, where can we find the hydrocarbons? Now, many people think that we have a big pool of oil or gas somewhere in the subsurface. So that's partly true. Yes, we have hydrocarbons in the subsurface. However, they are not just freely floating. So it's not like a pool. Instead, they are inside the pore spaces of the rocks. So we have rocks which are made up of several grain particles. Between the grains, let's say over here, you have pore spaces or just empty spaces. So these spaces will be filled with the oil and gas, or it could be also something different than hydrocarbons, maybe just pure water. So from a petroleum engineering perspective, we have two main parameters which are of great importance to us. First, that's the porosity, and second, it's the permeability. So porosity as a definition, it is just the percentage of the void spaces we have, or empty spaces within a rock, divided by its bulk volume. So that's how we can find porosity. Now, why is porosity important? Because it can give us an idea how much hydrocarbons are stored within this kind of rock. Second important parameter is the permeability. So permeability, it is a measure of the ease of the fluids passing through a rock. So let's consider these two samples over here. The black part, that is the grains. So this is solid parts. The white one, that's the empty spaces. So if we have a fluid trying to pass from the left towards the right, in this case, you can find it passing easily. So there is enough space for it to pass from one location to the other. Hence, we have a good permeability. However, in this figure over here, you can see that the grains are more connected to each other. The pore spaces are kind of disconnected. So if we have a fluid from this side and it needs to pass to the other side, it's going to be very complicated. So it's going to pass to this area, then it's going to be blocked by the grains. So in order to pass to the other side, it needs a complex direction. Hence, the permeability is going to be poor or low permeability. So what does that tell us? So if we have high permeability reservoir or just high permeability, then we can say we have a conventional reservoir. If the permeability was low, then we have an unconventional reservoir. If you look at this image over here we have a dark gray color. This is usually the source rock. In general, or in most cases, this could be a shale, let's say an oil-rich shale. So what happens is that this rock, it is an old rock. It is very deep and it is compacted. So whatever oil is produced there is going to migrate to a different location, let's say to a place over here where it forms a reservoir. Now what's special about this place is that we have a trap and a seal. So this gray over here, this is a seal. So the hydrocarbons will stay in this location and cannot move to the surface. Drilling in this location, you can find that the production is kind of easy because the fluids have high permeability, so fluids can move from the reservoir towards our wellbore and then up to the surface. If we are drilling in this location, then that will not be the case because permeability is very low over here. So even if we drill and we cross it, we're not going to have high production. So we need something additional in order to create the production we need, and that's what we call well stimulation. In this case, we are talking about hydraulic fracture. So differences between conventional and unconventional. At the top over here, we have a high medium quality reservoir. So what we mean by that is that this reservoir can easily be produced and it's going to give us a good quality in hydrocarbons. As you move down the triangle, you're going to find that we are entering, let's say, tight formations. If you go down, we're going to find gas shales or coal bed methane. Even further down, there's gas hydrates and oil shale. So in terms of permeability, as we are moving downwards, permeability is decreasing. So high permeability for conventional ones, lower permeability for the unconventional ones. Regarding the technology needed to produce the reservoir, so if it is just conventional one, then it's kind of easier to produce it. So the technology is just random. We don't need something very advanced. However, for the unconventional ones, then we're going to need a very high and advanced technology. So why are we talking about hydraulic fracturing and why is it important? So you know that hydraulic fracturing, it's one method to produce the unconventional reservoirs. And if you look at this map, it's showing us the location of unconventional reservoirs. So as you can see, it's spread around the world. So there's in the US, Brazil, Argentina, Middle East, Russia, China, Australia, and so on. So basically, you can find unconventionals almost anywhere in the world. If you look at the conventional ones, they're not shown in this image. However, the conventional ones, like most of them, have been already produced. Therefore, now the focus should be on the unconventional. So the future of petroleum engineers, it is more focused on the unconventional side, how we can produce them at the minimum cost and the least environmental damage. So for the time being, we have operations occurring in Canada, United States, China, and Australia. Other locations are starting the operation like Brazil and others. So what is hydraulic fracturing? Hydraulic fracturing, as the name says, it is fracturing or breaking down the rocks. How do we break it down? Through pumping certain kinds of fluids that we call fracturing fluids. So the applications mainly are to increase the flow rate of low permeability reservoirs, such as shale rocks, maybe coal bed methane and others. We also need to increase the surface area with the wellbore. So the wellbore is the bottom end of the casings which we have drilled, or the formation we have drilled. So as this wellbore is in contact, let's say, with more formation, then we can be producing even further hydrocarbons. It's also beneficial to reduce the number of infill wells. By infill wells, here we are referring to wells that are drilled in a certain location. So instead of drilling, let's say 5 wells in a certain block, now we just need, let's say, 1 well where we are doing a horizontal directional drilling and hydraulic fracturing as well. So one hydraulic fractured well can replace several other vertical wells. It's also used to increase the flow rates from the wells that have been damaged, like the skin that could form around the wellbore. This could be due to, let's say, drilling fluids that were not compatible with the formation, or due to any other reasons. So hydraulic fracturing in the US, it have increased the recoverable reserves by 30% for oil. So we are producing 30% more oil due to hydraulic fracturing, and 90% of gas in the US. So that's a very large amount, and that should have benefit the US much more in terms of oil and gas industry. Okay, I'd like to check whether you know the questions for these ones. So the first question I'm going to ask you is, when do you think was the first use of hydraulic fracturing? So I know we don't have a poll here, but you can maybe answer in the chat box.
1947.
So do you think it's 1917, 1947, 77, or 2007?
Muhammad, you can answer.
Well, I answered. I said 1947. It was in Kansas, but I'm not sure if that's the answer you're looking for.
Yes, that's actually the correct answer. Very well. So it was actually in 1947. That was when the hydraulic fracturing operation was tested by the Standard Oil company. It was in Kansas as well. However, I'm sure that you know that hydraulic fracturing became really famous more than in 2000s than in the 1940s. So we have some changes between 2007 and the 1947. Of course, that changes is due to the new technology we have discovered, new, let's say, fracturing fluids, new proppants. So all of that made it more be used in 2007 and onwards. So here's another question which should be fairly easy for you. Hydraulic fracturing, is it used to increase porosity or permeability?
Permeability.
Yes. The main aim of hydraulic fracturing, it is to increase permeability. Now, even if porosity increases maybe a little bit due to the additional fracture, but in the end, we're looking for permeability because that's what will help fluids to move from the reservoir towards the wellbore. So that's the correct answer. Okay, now we have completed the introduction part. We are going to go through the design part of hydraulic fracturing. First, I'm going to start with the fracture orientation. So here I'm more focused on the direction or the propagation of the hydraulic fracturing. In this figure, we have 2 different directions. We have a transverse fracture and we have a longitudinal fracture. So the difference between them is this one is extending in this direction, so it's moving further away from the wellbore, while the longitudinal fracture, as you can see, it is like along the wellbore itself, so it's making this kind of fracture, which is the light pink. So in general, which do you think we need more? Which is more beneficial to us? Is it the transverse fracture or the longitudinal fracture? What do you think? Is it the transverse fracture which we need, or is it the longitudinal fracture?
Transverse?
Yes, it is the transverse fracture. That's the one which we need. because we have a very low permeability reservoir, so we need to break it through as much as possible. So increase the extent into the reservoir. It's what the aim of hydraulic fracturing is. So how can we control this kind of fracture? How can we create a transverse fracture instead of a longitudinal fracture? In this case, we have to study or look back at the stresses in this region. So in terms of stresses, we can divide them into three main stresses. We have the vertical stress, which is sigma V. This is due to all the overlying rocks and formations. We have the horizontal stresses. It could be the maximum horizontal and the minimum horizontal stress. Now, for certain reasons, there's always a 90 degrees between them, between the maximum horizontal and the minimum horizontal. Same thing for the vertical stresses. So we have to look back during the drilling operation. So we have to drill right in order to get the transverse fracture. How do we do that? While drilling, we should drill in the direction of the minimum horizontal stress, which is sigma small h over here. So as you can see, this wellbore, it has drilled parallel to this direction. Hence, if we are going to fracture at this case, we are going to end up with a transverse fracture and not a longitudinal fracture. So what would happen if we drill in the maximum horizontal stress? So if this wellbore was going in this direction, parallel to this one, we are going to end up with a longitudinal fracture surrounding the wellbore. Okay, so that covers the fracture orientation. Now we are going to talk about the fracturing fluids. So we have different kinds of fracturing fluids. Everyone is going to be used or is used for different applications. So some of the most commonly used ones are the slick water, the cross-linked gel, and the foam. Foam, it's not really used for, let's say, shale reservoirs or deep rocks. It's more for shallow rocks. We are going to cover the slick water formation. So the main difference between slick water and cross-linked gel, it is the viscosity of our fluids. So this one has a low viscosity, whereas cross-linked gel has a higher viscosity. So it is the most commonly used in shale plays, and we can divide a slick water frac job into 4 steps. The first one, it is acidization stage. Here, we're not really focused on breaking the rock through acids. It's more focused on just cleaning around the wellbore. So we might have some formation damage, some skin. So we need to clear this area, make it more permeable in order for our fracturing operation to be more efficient. After this stage, we are going to go through the pad stage. By pad stage, we mean we are pumping the fracturing fluids at very high pumping rates. So for slick water, it's going to be somewhere around 70 barrels per minute. So at this stage, you're going to find that the rock is breaking quickly in complex directions. After a certain period of time, we are going to pump something we call the proppants. So what are proppants? They're almost spherical objects, usually sand, but could also be ceramic and other types. Those are pumped into the hole, and they're going to stay inside this hole or inside the fracture itself. So when we are going to produce this well, those proppants are going to keep this fracture open. So it's not going to close back on its own. After the proppant stage, we need a flush stage, and this is just to remove any additional proppants that are still left in our casing or in our tubing. So after cleaning our tubings from proppants, then we can say that, okay, this stage is done. We can move to the other stage and continue the operation. So if you look at this image over here, that's what our fracturing fluid might contain. So mainly it's water. So 88% is water, 11% that's sand. Sand here, it is the same as proppant. And the remaining around 0.5% could be other components, maybe gels, if we want to increase the viscosity a little bit, maybe friction reducers, So friction reducers, the aim for it is to decrease the frictional losses caused by the movement of the fracturing fluids along the casing or the tubing. So this movement is going to create some friction. Using this product, this friction is going to decrease a lot. Okay, now regarding the proppants, here you can see some of the proppants. They can be of different sizes. So we're going to look at some of the characteristics. The first one being the proppant size. You could have somewhere between 100 mesh up to 20 mesh in size. The mesh, it's a unit representing size. And for this case, the bigger the mesh value is, the smaller the size of the proppant. So 100 mesh, it's actually smaller than 20 mesh. This value is around 0.15 millimeters, and the 20 mesh is around 0.85 millimeters. So you can see how small those proppants really are. We also have the proppant type, as we have mentioned in the previous slide. So they could be ceramics, they could be sands. The proppant shape. So we're going to look mainly at the sphericity of the proppant and the roundness of it. Regarding the sphericity, it's more like representing a sphere. So it's not elliptical in shape, it's spherical in shape. The American Petroleum Institute, which is the API, it recommends certain values for sphericity and roundness to be above 0.6 for sand proppants and above 0.7 for ceramic ones. Roundness here is referring to how round the proppant is. So it shouldn't be angular at certain size, it should be as round as possible. We also have the crush resistance. So crush resistance here is going to be dependent on the closure stress of our reservoir. So we don't want the proppant to break down during production. We need it to withstand all the stresses. Therefore, it should have a sufficient crush resistance. Also, we have the specific gravity of the proppant, and that depends on its density divided by the absolute density of water. Okay, I'm going to also mention fracture conductivity. Now, this term is really important for hydraulic fracturing because it is directly a factor, or it's dependent on the permeability and the width. So what's KF over here and what's WF? If you look at this image in here, we have several proppants making several layers. Here we have 4 layers. These proppants are going to have a certain permeability. If they were opaque, they're going to have a permeability, and here it is KF. WF, this represents the opening of the fracture. So that's how wide the fracture is. So if we multiply those terms together, we get fracture conductivity, and this is in millidarcy's feet. If fracture conductivity increases, this means that the fluids can more easily pass from the reservoir towards our wellbore. If this is low, then our well stimulation might not be very efficient, and we should look for other means of improving the stimulation. So here we have an experiment that was done on 3 different types of proppants. We have the white sand. So this is just an uncoated sand. We have a resin-coated sand, and we have the ceramic ones. We were measuring conductivity as a factor of closure pressure. So as the pressure increases, obviously that the conductivity or the permeability is going to decrease a little bit because the width is going to decrease with pressure. So what happens is that the white sand showed the lowest conductivity of all the other cases, and it's decreasing rapidly with closure pressure. Ceramics are showing the best conductivity along with closure pressure. So we can deduce from this experiment that the ceramic ones are much better in terms of strength in maintaining conductivity compared to the other 2, the resin-coated and the white sand. Regarding the numbers over here, we have 40-80, that's the 40-80 mesh. Here 40-70 and 40-70. So the largest proppant in here, it's the 40 mesh.
We have different kinds of proppants.
So we can deduce that.
Just regular uncoated sand.
Okay, so we can deduce that the highest conductivity it is for the ceramic proppants, and the ceramic proppants, they are manufactured product. So we have some companies, they are going to manufacture those ceramic ones. They're going to control the sphericity for them. They're going to control the roundness and of course the strength. So all of that is under control. They are also thermal resistant. So you know that we have high temperatures in the reservoir. So those proppants are not going to be affected by these temperatures, and they're not going to undergo any degradation. The other proppants, we have the resin-coated ones and the sand. Sand being of the lowest conductivity. It's just a naturally occurring product. So strength is very low and it's going to be irregular in size and shape. With time, sand might undergo some degradation depending on, let's say, the chemicals included in the fracturing fluid and maybe the pH of the formation. Okay, here we're going to talk about dimensionless fracture conductivity. So how is this term different than the other fracture conductivity? This one is just a ratio. So here it doesn't have a unit. Okay, let's look at the figure and then we're going to talk about the equation. So here we have a hydraulically fractured operation. The gray one represents our fracture. The width of this fracture, the opening for it is going to be WF, which is shown in this equation over here. Regarding the extent of the fracture, so how far did it propagate into the formation, that's going to be 2XF. So from one location, it's just XF, which is over here in the equation. KF represents the permeability of the fracture, whereas K represents the matrix permeability, or the permeability of the formation before undergoing the hydraulic fracture. So if you're going to apply this equation, you're going to find that the top part, or the numerator, it's just representing the fracture. So the KF, the permeability of the fracture, and its width. Whereas the second part is representing the matrix permeability and the extent it is in contact with the fracture itself, which is XF over here. So if this value was 30 or above, this means that we have an infinite conductivity fracture. This tells us that our fracture is highly efficient, is going to be performing greatly. So we're not going to have, at least for the time being, we're not going to face any problems with our fracture. If this value was lower than 30, then it's just a finite conductivity. So we didn't reach the perfect case for a fracture, hence maybe additional stimulation might improve the results. So we can use this term to assess our fracture. Is it perfect, is it efficient, or maybe it needs additional work. Okay, here we are going to look at the multi-stage completion. So what's the multi-stage completion? That's basically dividing our fracturing operation into different stages. So we are going to fracture one stage, prepare it for production, move to other stage, and so on. Let's assume we have this is the rock, we need to fracture it, and the gray part over here, that's our casing or liner. First, we need to enter our perforating guns. Those three over here are the perforating guns. We have to enter them using the wire line. We set them at the location of interest, and then we are going to apply. We're going to apply the pressure. So the gun over here is going to perforate this area. So now we have access to the reservoir. As you can see through here, we have access from the well to the reservoir. Once we finish this area, we can move to the next stage. So here we have fractured basically the reservoir. We have applied the acidization stage, the pad stage, the proppant stage as well, and probably the flush as well. After that, we can move on to finish other stages. So for this case, this is the first stage. Once we do it, we move to the second one. We complete this part, move to the third, then the fourth, and so on. So for this case, we have 6 stages, and we have 3 clusters. So what are the clusters? Those are depending on the number of perforation guns that were used. So it's like every perforation gun is going to give us a cluster. So for this case, we have 3 clusters per stage. Okay, just before I continue, this is called the plug and perf operation. We also have other methods like using a sliding sleeve. So sliding sleeve, this represents a tubing or a casing which already has the holes in it. So we really don't need to use a perforating gun for this case. We just need to use certain technology to move the sleeve in order to have the opening of the casing facing the reservoir of interest. However, the sliding sleeve requires more experienced rig crew and advanced technology, so some companies prefer to stay with the plug and perf operation. Okay, so what about the environmental impacts? Now, many people think that we have to make a choice. We either have to produce the oil and the natural gas from the unconventional reservoirs, or we have to protect the environment, the public, and the safety. So it's really not that case. So it's not like we have to choose either produce the oil and destroy the environment, or save the environment and lose the oil. No. In order to more understand the problem here, we have to look at the factors which contribute to environmental damage. So if you look at this area, we have a well which fractured the reservoir. We have the freshwater zone somewhere near the surface, and it's always the case that the freshwater are close to the surface. If you look at the distance between the freshwater and the hydraulic fractured well, you can see that it's in red over here, representing a very large distance. So this could be like 2,000 meters or even more than that. It's very deep. So logically, it's not going to, let's say if we have hydraulic fracture, the fracture is not really going to extend directly to the freshwater zone. That's just not very logic, and several experiments were done, and they found out that the microseismic activity is just somewhere near the fracture itself. It doesn't extend that far towards the surface. Now we have 2 main problems that might occur. The most common one, it's due to the failure of the cement or failure of the casing in sealing the well itself. So what we mean here is that we might have some kind of leaks, micro leaks in the cement or in the casing joints. So everything we are producing, it might leak somewhere towards the freshwater zone. Now there are many factors that can increase the possibility for this, like the hydraulically fractures. So we have some vibrations going on, and they might affect our cement quality. So that's more like a problem with the cementing operation and the cementing integrity. So this can be avoided if we plan our drilling operations, especially the casing and the cementing part, really carefully, and we prepare to seal this area very well. So if this was done, then we're not going to have a problem with casing or cementing leaking up. The other problem, which is not really that common, but it might be occurring if we have an old fault plane. So let's say here we have a fault. So this place is not very stable. It might move depending on the pressure it's exerted to. So if we apply hydraulic fractures over here and it intersects the fault plane, it might give it enough push for this fault to occur. So it's like a small earthquake is going to occur at this area, but this earthquake might be strong enough to create a pathway from the bottom towards the surface for the freshwater zone. So if this happens, yes, you might find the gas leaking upwards towards the freshwater, and then it's going to contaminate it. However, this is not really that common. Mostly the problem is with the casing and the cementing operations. So let's summarize what we have covered in this lecture. So first, we've talked about the conventional and the unconventional reservoirs. We have shown that they are completely different in terms of the requirements. So conventional ones, you can easily produce them without using, let's say, high or strong stimulation methods. Unconventional ones require heavy stimulation methods like the hydraulic fracturing, which we already discussed. We have covered the fracture orientation, so how the fractures are extending within our reservoirs, in which direction they propagate. The fracturing fluids and the chemicals used, this was also discussed. The types of proppants, their characteristics, it was discussed as well. Fracture conductivity, this is a very important term for assessing our simulation method. Is it efficient or not? Most of the research or the experiments in this area use a conductivity cell. And this conductivity cell measures the fracture conductivity under several different scenarios. So these scenarios might be like changing the proppant type, changing the proppant size, the concentrations, maybe using different fracturing fluids. So that's why this term is very important. We have also covered the multi-stage completion technique for the plug and perf method. We have also mentioned that we have other methods, which are the sliding sleeve one. We have also covered the environmental impacts. So what has not been covered yet? We have the proppant, fluid, and rock interaction. We have not really covered how those three things interact together. So what kind of proppant should be used with which type of fluid? How will they interact together? Or what would the effect be on the rocks? So this subject is really big by itself, and you might cover it in another webinar. We didn't cover well placement. So let's say we have more than one well to be hydraulically fractured. So how are we going to place the wells? How far from each other should they be placed? Are there any certain standards to be followed? We also didn't cover stage spacing and cluster spacing. Those are also important topics which would affect the efficiency or the productivity of the wells themselves. So those topics are more considered like advanced topics for hydraulic fracturing, but we can maybe cover them in other webinars. But for now, that should be enough for the introduction of hydraulic fracturing. So
Thank you so much,
thank
Dr.
you
Kamel.
for attending this webinar.
Thank you so much, Dr. Kamel. And for sure, we'll have a second webinar discussing the points that you have mentioned now. And now we'll have the Q&A session. Some have written their questions in the chat section, and I'll say the questions now. We'll start with Hassan Khalifa. When we are dealing with a dimensionless fracture conductivity having a value higher than 30 millidarcy per dot feet, would that be an indication of a longer productivity life of the reservoir?
Okay, regarding the dimensionless fracture, if we have a value larger than 30, then yes, that consider that our fracture is very productive. However, that's not the only factor to look at for productivity life. We should also look at the permeability of the reservoir itself. So let's say for the first few months, we are going to produce everything which is within these fractures. After these months, we're going to look at the permeability of the formation. Is it of high permeability enough to be produced, or is it very low that the production is going to directly end? So this question depends mainly on the formation we are fracturing and the surrounding wells that have fractured the formation as well.
Okay, thank you. Farah Sahyune, permeability here is the Darcian permeability, the ease at which fluid can flow different from the intrinsic permeability in square meter. It might change slightly because of mechanical stress due to cracking process. Farah was answering a question that Ayman was asking. Ayman was asking, you asked at the beginning of the webinar that hydraulic fracturing increases permeability, not porosity. Then you said that it increases conductivity.
Yes.
So he was asking, why did you at first say that it increases permeability, not conductivity from the beginning?
Okay, regarding this thing, first of all, when we fracture the well, we have actually changed the formation. So before fracturing, we were talking about the permeability of the rock, which is supposedly very low because we're talking about unconventional well. However, when we fracture this well, we have replaced the rock with proppants. So those proppants are going to fill these spaces. And if you're going to look at the permeability now at the same location, you are going to find that this permeability is larger than what was previously there, which is the rock. So that's how the permeability is going to increase. But usually when we mention permeability and conductivity, we're just looking at the ease of the fluids to pass from one location to the other. So if permeability increases or if conductivity increases, this means that the fluids can easily pass within this location.
Okay, thank you, Doctor. We still have a couple of questions. Hamad Balushi is asking, in terms of volume of proppant per fluid that is pumped into the fractures, curious on your view of whether there is a particular rule of thumb for quantity in terms of pound meter, or is it contingent on the resource and depth per specification of the wellbore and reservoir tightness? In case you found the question is long, please, can you read it from the chat?
Okay, which one?
Muhammad Balushi.
Okay.
Yes.
Okay, like regarding the quantity of proppants, it really depends on the type of formation you are drilling or you are fracturing. It depends on the size of your fracture. So if you have fractured a big one, so we have a large geometry for our fracture, then of course you need larger amounts of proppants in order to fill most of this fracture. However, I can't really give you an exact value for pounds because every reservoir, every operation differs from the other. Regarding depth specification of the wellbore. Okay, usually we look at the mechanical properties of the rock. So the rock could be behaving like a ductile rock, or it could be a brittle rock. So by brittle means it's going to be fractured very easily. It's going to break down into pieces, and this fracture is going to elongate very far from the wellbore. In this case, we are going to use lots of proppants of smaller size in order to reach the extent of the fracture. If we have a ductile formation, then the fracture is not really going to be that big. It's just going to be surrounding our wellbore. Therefore, the quantity is not going to be that high.
Okay, thank you, Doctor. And now we have Brahim. What problems might be encountered during production?
Okay, during production, first thing, the closure pressure is going to be increasing. So the fracture, first it was filled with the fracturing fluids. The fracturing fluid was kind of holding the fracture apart. When we are starting producing the fluids, you're going to find that the closure pressure increases on the proppants that are inside. So we have several scenarios. Assuming we don't have another hydraulic fractured well nearby, we could have maybe proppants crushing down if we have a very hard formation, or if the proppant degraded over time. We might have an embedment problem where you can see the proppant like it's being imprinted inside the rock itself. Hence, the fracture might again close down and surround the proppant itself. So we have many problems could be encountered, but everything has its own solution.
Okay, and now Mahdi is asking, why is it that slick water is mainly used in fracturing more than any other fluid?
Okay, so first we have said that slick water, it is of lower viscosity than the gel ones. Because it's of lower viscosity, this allows it to move through tinier pore spaces. So this can create larger fractures. It can extend further into the reservoir, breaking it apart at further areas. Once this happens, then we can have a larger fracture, larger geometry, and hence we can have more productivity over time.
Okay, our last question from Farah. What is the maximum rate of oil recovery from the unconventional shale produced by hydraulic fracturing? This is the first question.
Okay, so the maximum rate of oil recovery from unconventional shale, I can't really give you a certain value for that. It also depends on the formation, how many clusters we have broken down, how many stages it is, what's the tubing size we are producing from, what are the regulations within this area. You know that regulations force the wells to produce at a certain rate and not exceed a certain rate. So we have too many cases affecting this value for the maximum rate. Okay, yes, that's the answer.
Okay, the second question. What is the technical difference between hydraulic fracturing for natural gas production and oil production?
Okay, regarding natural gas production, you know, the gas kind of can be produced easier. The gas can be lifted upwards of the surface without much, let's say, additional forces inside the reservoir. If we can break down the rock itself, then the gas is going to kind of be produced directly towards the surface. Now, for gas, we also have other issues, which are the adsorption within the grains, within the surrounding areas of the grains. So the gas kind of, it's going to, let's say, apply non-Darcy's law. We have several laws for the fluid flow. So it's not going to apply Darcy's law for the gas. For oil, it's going to be actually more challenging depending on how it's located, whether we're talking about shale oil or oil shale. So, you know, we have some difference between them. One of them, it's like having the organic matter inside the rock, but they have not really produced the oil yet. The other one, we have the oil already in the pore spaces. So, yes, if we're going talking about the difference between shale oils, then that's a big difference. And oil shale are currently like unproducible for our technology. We need additional technology to allow it to be more productive.
Okay, thank you so much, Dr. Kamel. It was a great webinar. And we are hoping for a second one discussing the topics that you didn't mention today. And thank you so much for your time. And thank you everyone for attending this webinar. Hope to see you next time.
Thank you, Doctor.
Thank you so much.
Okay, you're welcome.
Thank you.
Bye-bye.
Thank you. Bye-bye.